How many responses do you really need? I get this question a lot. This simple question is a never-ending quandary for researchers. A large sample can yield more accurate results, but depending on the research that you're doing, getting more and more responses can be quite expensive. So we want a sample that will get us the most bang for our buck, one that limits data collection expenses but still has sufficient power to draw accurate conclusions about a population. Based on what you just learned about confidence intervals, you might be able to see how we can reverse engineer that equation to get a formula that will yield the sample size needed to achieve your desired level of confidence and that reflects the level of error that you're willing to tolerate. Suppose we want to be 95% sure that X bar is an accurate estimate of the population with an acceptable level of error, or E. How large does the sample size need to be? We simply multiply the standard deviation and the critical value associated with our desired level of confidence, for example, 1.96, divide by the error that we are willing to accept, and then square the result. Note that this requires knowing the population standard deviation, which we rarely do. If you don't, use the standard deviation from previous research if available. What standard deviations are people who are conducting similar research reporting? Use that information to guide the standard deviation that you use in this calculation. Let's look at an example. How large does our sample size need to be if we want to be within 20 miles of the yearly mean for the typical hiker with a confidence level of 99%? We know that the standard deviation from previous studies is 52.63. Using a confidence level of 99%, our critical value is 2.576. So we multiply this value and the standard deviation, divide by 20, our error, and then square that value for a result of 45.95, or 46 people. But if you want to be within 10 miles, this number increases to 184. The more precise you want to be, the larger the sample needs to be. Here's how this works for proportions. You multiply the square of the critical value by P and Q and divide by the error squared. Again, this assumes that you know the proportions in your population. But in most cases, because the research hasn't been conducted, there is no value for the sample proportion. P and Q can then be taken from a previous study if one is available. If there is no previous study or estimate that can be used, use 0.5 for P and Q, because these proportions will result in the largest sample size estimate from this formula. Erring on the side of a larger sample is always better. Let's imagine that we want a result to be within 5% with a confidence level of 95%. Given that our confidence level is 95%, we know that the Z is 1.96. Let's assume we don't know the population proportion or the sample proportion, so we'll use 0.5. In this case, 1.96 squared multiplied by 0.5 times 0.5 and then divided by 0.05 squared gives us a result of 384.16, meaning that we will need 385 people to be 95% confident that our result is plus or minus 5%.